Hello everyone. In the previous video, we saw how a current carrying conductor was actually creating a magnetic field around the conductor through which it was passing through. Okay, so it was the magnetic field lines around a current carrying conductor that we saw. And when it was passing through a straight rod, when we are using a straight rod and when current was passing through it, the field lines were more like a circular fashion. The pattern of the field line was more of a circular pattern, right? As you can see in both the pictures, the positive terminal to negative terminal, the conventional flow of the current is this. That means the flow of the magnetic field line is clockwise. When we change the direction of the current, right, in the other opposite direction, the field lines also change their direction anti-clockwise, right? So that means the direction of the current flowing and the alignment of the magnetic field lines are interconnected. And we also saw how the current flows through the magnetic field lines are arranged due to the current flowing through the loop, right? And we use the right hand thumb rule, where the right hand indicated the flow of the current and fingers which were wrapping the conductor were representing the field lines, in which direction the field lines will be flowing, right? Now, an electric flow flowing through a conductor produces magnetic field. That is what we saw in the conductor, which was straight, and in the loop. The field so produced exerts a force on a magnet in the vicinity of the conductor. What does that mean? That means the current which is passing through the conductor kind of applies a magnetic effect or a force due to which the magnetic field lines are produced. So here we are going to understand the relationship between electric current, magnetic field lines, and force. It was French scientist André Marie Ampere who suggested that the magnet must also exert an equal and opposite force on the current carrying conductor. So there is a kind of a force which is applied between both magnet and electric conductor, with, as we say, Newton's third law, equal and opposite. Maybe there is a type of force which is existing between the magnetic field line and the current carrying conductor. That is what Andre Marais said that. And some way that force which is applied by the conductor is the reason why the magnetic field lines are formed. So let's look at the force which will be applied by the magnet on the current carrying conductor. So the topic that we are talking about right now is the force that is applied on the current carrying conductor in a magnetic field. We'll look into the activity first, and then we'll further understand what happens. Okay, and which rule we'll use to explain the relationship between the magnetic field, current carrying conductor, and the force. Clear? Let's look into the activity. So let's look into the setup. As you can see, there is a horseshoe magnet and a thin rod wire is being suspended by using two copper wires. This copper wire is connected to the positive terminal, and the other copper wire, that is the front end copper wire, is connected to the negative terminal. So let's look into the experiment. What happens when the current is allowed to pass through the wire and this rod which is placed between the magnet, and when the current passes through it, what is the direction in which it moves is what we are trying to figure it out. So what is happening? The wire which is connected is going to the negative terminal, right? Which is the first end of this rod, and the second end of the rod is with the positive terminal, right? The thin conductor. So this is now the current will be passed through this, right? So this is the positive terminal and this is the negative terminal, north, south. Okay, the moment the current is being switched on, just look at where the wire is going to move, the thin rod, right? So there is a magnetic force which is going to apply between north and south, and there will be the current flowing. So now when we switch on, let's observe what happens. It is perpendicular. The moment it is being switched on, it should move either to the left or the right. That's what we are expecting to move. Okay, so let's see when the switch is put on. Its deflection towards the right, right? Let's try it once again. Let's put it on, and it is deflecting towards the right. So what happened? The current is flowing through this positive terminal and it's passing through this conductor and moving away. At the same time, there is a magnetic field which is flowing between the north pole and the south pole. So the current is flowing from here, the field is going from here to here, right? So because of these two influences, there is a force which is applied on the wire and it is deflected towards the right hand side. Okay, the rule that we use is what we are going to look into. Like we use the right hand thumb rule to understand which is the direction of the force when there is a electric current flowing through the conductor, then which is the direction of the magnetic field lines. The same way we use a rule to find out if there is a current flowing through the conductor and there is a magnetic field present at the same time, in which direction the force will be applied. Before we go into that, let's look into the theoretical part of this experiment and then we'll go for the detailed rule and how to apply it. So the same arrangement, point A is connected to the negative terminal and point B is connected to the positive terminal, and this is the north and the south, right? So when the current was, this is north and this is south. When we switch it on, when the key is pressed on, what happens? The rod is moved towards the left hand side, right? When we switch it over, means if I just connect this battery in the other direction, in the opposite direction, right? That means the positive and the negative terminals are changed. Then the motion or the force of the rod will be in the right hand side. Clear? Then if I don't touch the battery, that is, I'm not changing the connection of the battery, but I'm going to shift the horseshoe connection where the north is downwards and the south is upward. That means I'm changing the direction of the magnetic field. Then again, the rod is going to deflect in the right hand side. So here, when I change the direction of the current flowing through the conductor, the direction of the rod in which it is being pulled or the force applied will be on the opposite direction, that is on the right side. Whereas if I'm shifting the magnetic pole, if I'm changing the magnetic poles, then also there will be a change in the direction in which the force is applied. So clearly the displacement of the rod in this activity suggests that a force is applied, okay, on the current carrying rod which is placed in the magnetic field. It also shows that the direction of the force is reversed when the direction of the current through the conductor is reversed. So I just mentioned, if I am reversing the direction of the current, then automatically the rod will be moving towards the right hand side. Similarly, if the pole of the magnet are interchanged, then the direction of the field will be vertically downwards, or here in this case, yeah, it's upwards, right? It is up to down. Initially it was up from north to south, which is downwards. Now I'm shifting it vertically up. Then in this case, the direction of the force will also get reversed. So how can we reverse the rod movement of the rod? By either changing the magnetic field direction or by changing the current. So therefore, can we say that the direction of the force applied on the conductor depends on two things: in which direction the current is flowing and which direction the magnetic field is applied. So the displacement of the rod is largest when the direction of the current is at the right angle and the direction of the magnetic. Now, yes, as we know that the force is depending on two things: direction of the current and the direction of the magnitude. Now, if we want the maximum displacement to occur in the rod, then the only way that we can do is if we allow the direction of the current to be exactly perpendicular to the direction of the magnetic field. Then the rod will have the maximum displacement. If the direction of the current and that of the magnetic field are perpendicular to each other, then the movement or the force by which the rod is going to displace, the direction in which it will get displaced, is also perpendicular to both of these. Okay, so to understand this last section, that what I'm trying to explain here is the current has one direction, then the motion will be in the other direction. So let's say the current is in this direction, right, and the magnetic field is in this direction. So they are perpendicular to each other, right? Then the force which is applied on the rod will be perpendicular to both of them. If you look into it, this is also 90 and this is also 90. That is what this rule is talking about. And the rule that we use is called as Fleming's right hand thumb rule. Right? So stretch the right thumb. It's Fleming's right hand, so use the right hand rule. Sorry, it's not the right, it's the left hand rule. As the picture shows, you have to take your left hand. Okay. The thumb, you have to stretch it. It's going to represent the direction in which the force will be applied. The first finger will always represent the direction in which the magnetic field is applied. and the middle finger is going to show the direction of the current. Again, the thumb is going to show you the direction of the force. The first finger is going to show you the direction of the magnetic field. The middle finger is going to show you the direction of the current. So if you hold the hand like in front of the screen, you can see that the force and the current are in perpendicular, means there is a 90-degree which we can draw. Similarly, there is a perpendicular line which there is a 90-degree, or they are perpendicular, which to force and magnetic field. Same way, force and current is also 90-degree. Correct? So you have to stretch your fingers in such a way that you can clearly see the 90-degree. Correct? The first finger points to the direction of the magnetic field. The second finger points to the direction of the current. That is the second finger. And the thumb will always show the direction of the motion. Clear? Let's look into the activity again and try to find out the direction. Whether the rod which shifted to the right actually followed this rule or not. That is the Fleming's left hand thumb rule. Okay. Now keep your hands left hand ready with you. The flow of the current is from extreme end to the right. So it's going from it's coming out to be basically it is coming out towards us. That is the flow of the current. Okay, so your second finger should be pointing towards you, right? The magnet is placed in such a way that the north pole and the south pole, so the north and the south, so you have to go down, right? Because the magnetic field is always the first finger. So first finger you should point it downwards. So you should shift the finger in such a way that the finger goes downwards, and the second finger should be pointing towards you. Now look at the thumb where it is going. The experiment is also going to show you the same thing, right? So keep holding your left hand and understand how it is going. So can you see the current, which is the second finger? The first finger is the magnetic. So this is how you're supposed to hold it. The second finger pointing towards you, the first finger pointing downwards. So the thumb is moving to the right hand direction. So now when you put the switch on, you can see the rod moving to the right hand direction, right? That is the thumb, which is indicated by the force, right? So let's switch on and let's see whether the rod is moving or not, right? So let's see what happens. So can you see the rod just move towards the right? Now switch it off, it's going to go back. Again, it's going to go towards the right. Now we are going to change the direction of the magnetic field. Means we are going to place the magnet in the opposite direction, the south pole up and the north pole down. And we are going to look at the direction of the wire. Again, applying the Fleming's left hand rule. So now in which direction the magnetic field is going to go? Bottom to top. So your first finger, the first finger should go up, right? The middle finger should be again towards us, right? So thumb will be pointing towards the left. See, the second finger is towards us because the current is from there to there, right? From there to there. And the first finger is going to go upwards because north to south. So the thumb is pointing towards the left, right? Clear? Try holding your left hand and try to see. And can you see the rod moving towards the left? Yes. So this is how the force can be detected. So Fleming's left hand rule helps us to find out the direction in which the force will be applied if electric current and magnet both are placed near it. Okay, this particular concept is used in many devices like electric motors, electric generators, loudspeakers, microphones, and measuring instrument. For a quick recap, now here if you can see the picture, the magnetic field is going from bottom to top, right? So hold your first finger in such a way that the finger is moving upwards. The current is moving to the left to right, kind of diagonally. So hold the current moving from left to right, the middle finger. So you just have to twist your hand in such a way that the thumb is towards you. So the force is towards you, right? Again, hold the first finger of your left hand in such a way that it is moving upwards. So this is what will happen. This is the magnetic field. This is the current and the force is moving out, right? Hope it is clear. Thank you.